Gravity is an ancient, invisible cage. For the entirety of human history, the mass of our planet has anchored us to the ground, turning the vacuum of space into a physical barrier that requires immense energy to breach. In the early 2000s, an isolated proving ground on the edge of the world became the staging area for a direct assault on that barrier. This is Omelek Island, a remote sliver of coral in the Kwajalein Atoll. Sitting on the launch pad is the Falcon 1. It was designed from scratch by a small, untested private team attempting to build a viable orbital launch vehicle. Breaking the grip of Earth's gravity requires absolute precision. The laws of physics dictate that a single millimeter of misalignment or a fraction of a second in delayed timing is enough to turn an orbital vehicle into falling debris. That reality materialized on March 24, 2006. Less than a minute into the Falcon 1's first flight, a localized fuel line leak ignited a fire in the engine bay. The vehicle pitched sharply and slammed into a dead reef just 41 seconds after liftoff. The second and third attempts exposed entirely different vulnerabilities. During Flight 2, an interstage fairing bumped the upper engine bell, inducing a circular coning oscillation that amplified until the rocket tore itself apart. This diagram illustrates the physics that doomed Flight 3. Staging occurs exactly as planned, but residual fuel inside the new Merlin 1C engine evaporates. This creates a momentary burst of thrust, pushing the discarded first stage forward. The heavy lower stage slams directly into the delicate second stage, instantly crippling the trajectory and ending the mission. By the fall of 2008, the company was weeks away from total bankruptcy. The components for a fourth rocket were assembled on Omelek under the knowledge that another failure meant the end of the entire enterprise. On September 28, 2008, Flight 4 performed flawlessly. The Falcon 1 reached orbit, becoming the first privately developed, fully liquid-fueled launch vehicle to achieve the milestone. Yet, despite the triumph, the existing economic model of spaceflight remained intact. The multi-million-dollar rocket was still destroyed upon re-entry. Pushing mass to orbit continued to be an absolute drain on resources, requiring a new vehicle for every single launch. By 2012, operations expanded to a testing facility in McGregor, Texas, to address the core problem of disposability. Engineers shifted focus to a secondary challenge, reversing the physics of ascent to land the hardware safely. Vertical takeoff, vertical landing, or VTVL, was the tool selected to solve this problem. If a first stage could return to the launch pad, the cost of spaceflight would drop by orders of magnitude. The experimental vehicle was named Grasshopper. It consisted of a 10-story Falcon 9 first stage tank, a single Merlin 1D engine, and a wide stance of 4 steel and aluminum landing legs equipped with heavy hydraulic dampers. In September 2012, Grasshopper completed its first major milestone, a test hop of just 6 feet. The altitude was minor, but it proved the engine could be throttled with enough precision to briefly counteract the vehicle's immense weight without launching it out of control. Firing an engine at maximum thrust to escape the atmosphere is a brute force calculation. Hovering that mass on a column of fire is a balancing act of delicate, real-time adjustments. It requires the physical equivalent of balancing a pencil on your fingertip during a hurricane. Over the next year, the test scaled up rapidly. By June 2013, the Grasshopper was lifting itself to an altitude of 325 meters before steadily descending back to its launch mount. The highest and most demanding leap took place in October 2013. Rising to 744 meters, the vehicle was programmed to execute a highly complex maneuver known as the divert. To execute the divert, the rocket maintains exact vertical thrust to hold altitude while simultaneously vectoring force to push itself horizontally. The flight computer gimbals the engine to prevent tipping, then applies precise counterthrust to kill sideways momentum and align perfectly over the target. The successful 744-meter divert proved the hardware could handle the stress. More importantly, it validated the computational logic required to tame gravity on descent, executing thousands of automated micro-adjustments per second. The control algorithms tested over the fields of Texas formed the architecture for the modern Falcon 9. The autonomous landings that are now a routine occurrence are the direct successors to those early experimental hops. Reusability alters the economics of space exploration. It replaces a disposable one-way system with a sustainable cycle, significantly reducing the financial wall that once prevented consistent access to orbit. The failures into the Kwajalein Reef and the controlled descents in McGregor belong to a single continuous process. They were the evolutionary crucible required to figure out how to reliably overcome gravity in both directions. Ultimately, lowering the barrier to orbit turns space from a destination for the few into a territory accessible to many. When reaching the stars no longer requires a total loss of the vehicle, the mission changes. Mastering the return trip transforms the rocket from a single-use projectile into a reusable ferry. This reliability creates the bridge between Earth and the rest of our solar system, allowing for the construction of permanent orbital infrastructure. Through these repeated, calculated acts of defiance against gravity, we are moving beyond the era of experimental hops. We are building the logistical foundation required for a long-term human presence among the stars.
Engaged, we can watch a 20-story rocket booster plummet from the edge of space, reignite its engines, and lower smoothly into giant mechanical catching arms. 15 years ago, doing this routinely was treated as science fiction. For decades, the aerospace industry followed a rigid doctrine: failure is not an option. To avoid disaster, agencies spent billions engineering vehicles to near perfection before they ever touched a launch pad. The result was highly reliable rockets that were entirely disposable, making spaceflight prohibitively expensive. As a privately funded startup, SpaceX faced a dual challenge. They had to reach orbit at a fraction of the traditional cost, and they had to figure out how to recycle the vehicle, treating a rocket more like a reusable airplane than a single-use mortar shell. The clock was ticking. The company was operating out of a bare-bones facility, and the entire venture was dependent on Elon Musk's personal fortune to keep the lights on. Their solution was an iterative engineering method that terrified traditional aerospace veterans. Instead of spending a decade simulating a perfect flight on a computer, SpaceX chose to build hardware quickly and launch it expecting it to explode, using the debris to learn exactly where the design failed. To test this high-risk approach, they needed a location where debris wouldn't threaten populated areas. They found it on Omelik Island, a tiny remote coral atoll in the middle of the Pacific Ocean. Here, they built the Falcon 1. Compared to the massive government rockets of the era, it was a relatively small experimental vehicle. This animated timeline tracks the rocket's first launch attempt. Everything is nominal until T+26 seconds, when a corroded aluminum nut fails. A fuel line leaks, igniting a fire that destroys the vehicle. They fixed the plumbing and launched again. As the timeline pushes toward 4 minutes and 20 seconds, a new issue emerges: severe aerodynamic coning oscillations. The sloshing liquid oxygen in the upper stage throws the rocket off balance, and telemetry ends. After adding baffles to stabilize the fuel, they attempted a third flight. Reaching the staging phase, the animation highlights a new error. Residual fuel in the engine evaporates, providing a burst of unexpected thrust. The discarded first stage slams directly back into the upper stage. 3 flights ended in 3 complete losses of the vehicle. But in an iterative engineering model, these were high-speed data collection exercises. Each catastrophic loss provided hard telemetry that forced rapid redesigns of their hardware and staging software. That hard-won data culminated in September 2008. The 4th flight of Falcon 1 was flawless. It became the first privately developed liquid-fueled rocket to reach Earth orbit, securing the NASA contract that saved the company from bankruptcy. Reaching orbit solved the upward problem, but to make spaceflight truly affordable, they had to stop throwing away millions of dollars of hardware into the ocean after every launch. The focus shifted from the Pacific to the plains of McGregor, Texas, providing a controlled environment to tackle the mechanics of coming back down. They built a test vehicle named Grasshopper, a repurposed 10-story Stalker 9 fuel tank outfitted with 4 heavy steel legs and a single Merlin engine. In September 2012, Grasshopper ignited its engine and rose exactly 1.8 meters into the air before settling back down. The short hop verified the absolute baseline of the control algorithms. The scaling was aggressive. Over the next year, they pushed the vehicle to 40 meters and then 325 meters. These flights stress-tested the closed-loop control system, proving the engine could throttle quickly enough to hover in midair.
This 3D vector graphic visualizes the 744-meter flight in October 2013. The vehicle performs an active lateral divert, shifting 100 meters horizontally before descending precisely onto a bullseye. Mapping this localized maneuver onto an orbital descent arc shows its true value. The divert proved that a rocket returning from space could actively steer through high-altitude crosswinds to hit a specific landing pad. Powered by a new suite of navigation software known as F9R, Grasshopper took vertical landing out of the realm of theory and turned it into a repeatable reality. Neither the Falcon 1 nor Grasshopper were intended to be commercial products. They were flying laboratories built exclusively to gather data. SpaceX took the orbital engine architecture of Falcon 1 and fused it with the hydraulic legs and navigation algorithms of Grasshopper, creating the Falcon 9. Today, the aerospace industry no longer discards tens of millions of dollars in precision machinery after a single use. Rockets fly and land multiple times a week. This modern standard was earned on a tiny Pacific island and a Texas field. By risking everything on those early tests, SpaceX traded 3 destroyed rockets for the specific telemetry required to build the world's first reusable fleet.